Differentiation of logarithmic functions. The natural logarithmic function y equals log base ex equals ln x, which is the natural log of x, is another key function in the theory of differentiation. Its derivative is given on page 25 of the formulae and tables. So if f of x equals ln x, which is the natural log of x, then the derivative f prime x is 1 over x. Implicit differentiation can be used to verify this derivative, as the following example shows. So here we have page 25 of our formula book, and here we have our derivative that we're looking at the moment. So if f of x is ln x, or the natural log of x, then f prime x, or the derivative of that, is 1 over x. So let's have a look at the example. If y equals log base ex, show that dy dx equals 1 over x for x values greater than 0. So if y equals log base ex, then e to the power of y equals x. So we're using our log statement from page 21 that says that if a to the power of x equals y, then log base a y equals x. So we can swap this around so that we have log base a y equals x, gives us a to the power of x equals y, and swapping the a for e, so this a for e, and the y for x, so this y for x, and the x for y, so this x for y. So if log base e x equals y, then e to the power of y equals x. Or we could use our scorpion tail method. So e to the power of y equals x. So using our scorpion tail method, e to the power of y equals x. So we have e to the power of y equals x. Now using implicit differentiation, so we want to differentiate with respect to x. So we differentiate both sides with respect to x. So differentiating e to the power of y with respect to x, well, there is no x, so we just differentiate with respect to y. And differentiating e to the power y with respect to y just gives us e to the power y. But we have to stick on a dy dx because we're using implicit differentiation. And then we differentiate x with respect to x and we get 1. So e to the power y we can swap for x because we stated that e to the power of y is equal to x up here. So we have x dy dx equals 1, and then solving for dy dx, we get dy dx equals 1 divided by x, which is 1 over x, which is what we wanted. So this is page 21 of our formula book, indices and logarithms, and this is the statement that we just used. So the natural log function can occur in products and quotients. So example 2, find dy dx if y equals x squared log base ex. So since x squared and log base ex are stuck together, we know that this means multiply, so we use the product rule. So x squared is the u and log base ex is the v. So product rule is u dv dx plus v du dx. So the u is x squared, so we just write it down with brackets. dv dx, so we're going to differentiate v, which is log base ex with respect to x. So we get 1 over x, so we just write that down with brackets, plus v log base ex, we just write that down, and then du dx, so we differentiate u with respect to x, so we get 2x, and then we multiply. So x squared by 1 over x gives us x, because you get x squared over x, which simplifies. We can cancel 1x on the top and on the bottom. So just to show you over here where I got that from. So x squared over 1 times 1 over x is x squared over x, which is x. So 2 minus 1 is 1. So x to the power of 1, or 1, x. And then log base ex times 2x is 2x log base ex. And then we can factorize out the x. So we get x times 1 plus 2 log base ex. Chain rule for natural logarithmic functions. The chain rule must be used to differentiate natural log functions of the form y equals log base EU if u is anything other than exactly 1x. So for example, we would need the chain rule to differentiate log base e 1 plus x squared, or log base e sine x plus 2, or ln x plus root x. Suppose y equals log base EU, then by the chain rule, dy dx equals d log base EU dx, which equals d log base EU du multiplied by du dx, which equals 1 over u times du dx. In practice, it is easy to say the chain rule or natural log functions. Put 1 over the value inside the log and multiply by differentiating the value. So, chain rule 5 for logarithmic functions. D ln u dx equals 1 over u times du dx. So basically differentiate the log multiplied by the derivative of the value. Example 3. Find dy dx if y equals log base e sine x plus 3. So y equals log base e sine x plus 3. So we're going to use the chain rule. So we differentiate the log, so this is the outside. So log base e, so if our f of x is ln x, or the natural log of x, or log base e x, the derivative is 1 over x. So we get 1 over sine x plus 3. So we keep the angle. 1 over sine x plus 3. We multiply that by the derivative of the value. So the derivative of sine x is cos x. The derivative of 3 is 0. So you get 1 over sine x plus 3. So we've differentiated the log. So this is the outside. Multiplied by the derivative of the value. This is the inside. And then multiplying 1 times cos x is cos x. And that's over sine x plus 3. The laws of logs can be used to simplify a log, removing the need for a product, quotient, or chain rule when differentiating. So for example, if we have log base e x to the power of 3, we can rewrite that as 3 log base e x, using this law, our third law of logs, from page 21. If we have log base e x sine x, we can rewrite that as log base e x plus log base e sine x. So this is our first law from page 21. And if we have log base e x over cos x, we can rewrite that as log base e x minus log base e cos x. So that's our second law on page 21. So rewriting like this, we don't need to bother using the chain rule. Rewriting like this, we don't need to use the product rule. And rewriting like this, we don't need the quotient rule. So always check if you can rewrite using your laws of logs to avoid using these. So here we have page 21 and all our indices and logarithm rules. So if y is equal to the natural log root x squared plus 1, find dy dx. So the first thing we want to do is rewrite as y equals the natural log of x squared plus 1 to the power of a half. And then we're going to rewrite again by bringing the half down in front of the log. So using this formula, or this rule from page 21. So we have a half ln, or the natural log, of x squared plus 1. So it basically brought the power down in front. So it's like we brought the q down in front, we brought the half down in front. So this is from page 21. So now we have a half natural log x squared plus 1. And now we can differentiate using the chain rule. So we differentiate the log and multiply that by the derivative of the value. So differentiating the log, so we still have the half, but that's multiplied by ln, which gives us 1 over x. So we have 1 over x squared plus 1. So we keep the x squared plus 1, we keep the x value. And then we multiply that by the derivative of the value, so the derivative of what's inside the bracket. So x squared plus 1, the derivative of 2x is 2x. So this is differentiating the outside, this is differentiating the inside. Now the 2's will cancel, and we end up with 1 multiplied by x, which is x, and x squared plus 1 for our denominator. Being able to differentiate natural log functions allows us to differentiate general exponential functions i.e. exponential functions where the base is not necessarily e. For example, consider the function y equals a to the power of x, where a is greater than 0, is a constant. Taking logs to the base of e on both sides and using implicit differentiation, we get log base y equals log base a to the power of x. So we're basically multiplying both sides by log base e. We're sticking on a log base e to both sides. Now log base e we can rewrite as ln. So we have ln y equals ln. So we have ln y equals ln a to the power of x. So we can bring the x down in front. So using this law, so log base a x to the power q equals q log base a x. So we're using this law from our formula book. So we basically bring the power down in front of the log. And we know that the natural log of y, if we want to differentiate that, is going to be 1 over x if it's with respect to x, but since we have a y, it's going to be 1 over y. So we're differentiating here using implicit differentiation. So if we are differentiating with respect to x and we don't have an x, we differentiate with respect to y and then we stick on a dy dx. So ln y, or the natural log of y, becomes 1 over x dy dx. Now this x here disappears because the derivative of x is 1, i.e. y equals x ln a, or natural log a. Then y prime, or y dash, equals 1 natural log a, because the derivative of x is 1. And 1 natural log a is just natural log a. So that's how the x disappears down here. So now we solve for dy dx. So we multiply both sides by y to get rid of the 1 over y on the left. So we end up with y ln a, or y natural log a. And we know y is equal to a to the power of x from up here. So we end up with dy dx equals a to the power of x natural log a. So this standard derivative is given on page 25 of the formulae and tables. So if y is equal to 2 to the power of x, find dy dx. Well, if f of x is a to the power of x, then f prime x is a to the power of x natural log a. So basically we just swap that 2 there. We swap the a for 2. So we're swapping both of these a's for 2 as well. So we have dy dx equals 2 to the power of x natural log 2. Chain rule for general exponential functions. The chain rule must be used to differentiate general exponential functions of the form u to the power of a, where u is anything other than exactly 1x. So for example, we would need the chain rule to differentiate 2 to the power of 3x plus 1, or 10 to the power of 3 plus sine x, and so on. Suppose y is equal to a to the power u, then by the chain rule, d a to the power u dx is equal to d a to the power u du multiplied by du dx, which gives us a to the power u natural log a times du dx. So chain rule 6 general exponential functions, d a to the power u dx equals a to the power u natural log a times du dx. So basically, differentiate the exponential and multiply it by the derivative of the index. So differentiate the outside and multiply it by the derivative of the inside. So find dy dx if y equals 5 to the power 2 plus 3 sine x. So y equals 5 plus 2 plus 3 sine x, then dy dx is 5 to the power 2 plus 3 sine x multiplied by the natural log of 5. So this is basically our outside, so we want to differentiate the exponential. So we differentiate 5 to the power of u, so 5 to the power of something, or in this case a to the power of x. So a to the power of x is our f of x, then f prime x is a to the power of x natural log a. So we swap both of these a's for 5. So we get 5 to the power 2 plus 3 sine x multiplied by the natural log of 5. So here we are differentiating the outside or differentiating the exponential. Then we multiply that by the derivative of the index. So the index is 2 plus 3 sine x. To differentiate 2, you get 0. And to differentiate 3 sine x, you get 3 cos x. So this is our answer. So again, it's the outside-inside rule. For the chain rule, we differentiate the outside. So we're differentiating the exponential multiplied by the derivative of the inside, the derivative of the index.